to be talking about the difference between a scalar and a vector, different vector operations, different forms of writing vectors, the unit vector, cross product, dot product, and more. So let's start with the difference between a scalar and a vector. A scalar is simply anything that just has a magnitude. For example, 5 kilometers, 3 p.m. A vector is something that has both magnitude and direction. For example, 5 kilometers north, 2 miles per hour up. The direction can be anything: north, south, east, west, northwest, east 5 degrees north, south 5 degrees west, up, down, left, right. Some examples of scalars include time, like 3 p.m., or distance, like 5 kilometers. Some examples of vectors include displacement, like 5 kilometers north, or velocity, like 2 miles per hour up. Note that when you write out vectors as variables, you need to put an arrow on top. Now that we know what a vector is, how do we actually represent it? What does it look like? Well, a vector is just an arrow. It can be a line with an arrow pointing in any direction. So all of these are considered to be vectors. Now let's talk about the different forms of writing vectors. The first form is just the magnitude and direction of the vector. For example, say we have a coordinate grid, and I have a vector v on my grid. Now this vector starts at the 0, 0 point, and I'm told that it ends at 4, 3. And the angle that it forms with the x-axis is 50 degrees. If we were writing a vector out using the magnitude and direction method, we would write it out like this. These absolute value signs, these parallel lines next to the vector v, or it could be called a, b, c, whatever your vector is called, these lines mean the magnitude of the vector, and the direction is going to be given by cos theta and sine theta. Sometimes you might see it written with double parallel lines. So let's call the beginning point P and the ending point Q. Now, in order to find the magnitude of PQ, or magnitude of V, we can now write it out as this. The equation is the square root of x2 minus x1 squared plus y2 minus y1 squared. Now, what is x1, x2, y1, and y2? Well, we are given two sets of coordinate points. Each of these have an x and a y value. So I just pick one point and label them x1 and y1, and the other point is x2 and y2. And then I plug these values in. x2 is 4, and x1 is 0. y2 is 3, and y1 is 0. I get 5. So that means that from here to here the distance is 5, meaning the magnitude of vector v, or vector pq as we now labeled it, is 5. Now we have everything we need to put it into magnitude and direction form. 5 cos theta is given to us as 50 degrees, so cos of 50 degrees, sine of 50 degrees. So looking at this notation, it tells you that you have a vector of length 5 with an angle of 50 degrees between the vector and the x-axis. Next, let's talk about the component form of a vector. The component form of a vector has the x and y components if it's in 2D, or the x, y, and z components if it's in 3D. The component form of our vector is 4, 3. Because 4, 3 means x, y, this means on the graph that we go over 4 points on the x-axis and up 3 points on the y-axis in order to reach our vector. Now let's talk about the last form of vector notation, which is using unit vectors. In unit vector form, it is almost the exact same thing as component form. Component form was in the form of x comma y, 4 on the x, 3 on the y. The unit vectors I corresponds to x, j corresponds to y, and k corresponds to z if you have a 3D vector. So the way we would write this out in unit vector form is by attaching 4 with I plus 3 with j plus 0 with k. We don't have to write this because we don't have anything along the z-axis. This vector is only in 2 dimensions. I always corresponds to the x component, j is the y component, and k is the z component if you have one. Next, let's take a look at what the unit vectors actually look like and where I, j, and k came from. Note that vectors can be one-dimensional, meaning just going along one axis, like this, just goes along the x-axis. They can be two-dimensional, like this vector, which goes between the x and y axes, or it can be in 3 dimensions, which is harder to draw, but imagine this 2D vector still starting at the 0, 0 point, and the tip is being lifted up all the way to here. So it's within the x and y dimension, but now it also has a height, so it's in the z dimension, and that would be a 3D vector. Unit vectors are vectors with a magnitude of 1, and on each axis, the x, y, and z axes, we have unit vectors I, j, and k. The coordinates for these unit vectors are as follows. I, which corresponds to the x-axis, has a unit of 1 along the x-axis and 0 in the other directions. So our unit vector is 1, 0, 0. J, which corresponds to the y-axis, has 0 in the x direction, 1 in the y direction, and 0 in the z direction. Similarly, the k unit vector corresponds to the z-axis and has 0 in the x and y direction and a unit of 1 along the z direction. These are the basic unit vectors, and all other vectors can be written as a combination of these unit vectors. So going back to our earlier example, where I had our vector 4, 3, we wrote it out in unit vector form as 4i plus 3j. What that means when you look at this graph is that it would be 4 units of 1 along the x-axis and 3 units of 1 along the y-axis. If I had a third dimension, such as plus 2k, it would be 2 units along the z-axis in order to get a vector somewhere in 3D space. Let's talk about the different operations we use to combine vectors. Now that we've talked about the unit vectors I, j, and k, we are going to find out how to convert any vector into a unit vector. So say we are given vector A, 2, 3, 4. The equation of unit vector A, which is A with the hat on top, just like the unit vectors I, j, and k, is going to be equal to the vector, which is given up here, divided by the magnitude of the vector. Recall that we talked about finding the magnitude, which is just the distance or length of a vector, and the equation was given as x2 minus x1. In the example we had earlier, we were dealing with 2 dimensions. In this case, we have an x, y, and z dimension because there are 3 numbers in this vector. So we are going to have to add z2 minus z1 squared to the end of this equation to put it into 3D. So although we are only given one vector, you might be wondering, how are we supposed to subtract when we are only given one vector? Well, your next vector, which let's call b, is going to be the 0 vector. So now let's call this x1, y1, and z1. And these are x2, y2, and z2. Now all we do is plug the values in. So we get the square root of 29, which is the magnitude of A. Now in order to find the unit vector, we divide each term in our vector by the magnitude. Now putting it into component form, we have 2 over root 29i plus 3 over root 29j plus 4 over root 29k. This is the unit vector of A, which is A hat. Vectors have multiple different operations that we can use to combine them. The first one is addition. Subtraction also falls under this because we don't subtract vectors, we only add negative ones. The second one is multiplication. Note that there is no division when we work with vectors. Instead, we multiply by fractions. There are three different types of multiplications that we can do with vectors. The first one is multiply by a constant. The second one is the dot product. And third is the cross product. Let's start with an example of adding and quote-unquote subtracting vectors. So let's go through adding vectors in one dimension. Say we have vector A pointing up, 5 meters up. And we have vector B pointing 3 meters down. Let's try the following questions. What is A plus B? And what is A minus B? When we add vectors, we add them tip to tail. Let's draw our vector A. We are going to draw vector B on top of it. So from the tip of A, we have to draw vector B, which is actually pointing right on top in the other direction. The overlapping area is the part that cancels out. And what's left over? 5 minus 3 is 2 meters. The answer is 2 meters. A different way to do this without drawing vectors tip to tail is simply put positives or negatives in front of the numbers based on their direction. A is 5 meters up, and that's positive. So we have a positive 5. Now we're going to add 3, but it's negative because it's pointing down. So 5 plus negative 3 equals 2 meters. And the direction, is it 2 meters up or 2 meters down? The direction of your answer is going to be the bigger number. Here, when comparing 3 and 5, our bigger number was 5, and the direction of 5 is up. Therefore, the direction of our answer will also be up, 2 meters up. Now, how would we subtract these vectors? Let's do it graphically and algebraically. So first, let's draw vector A one more time. And now, when we add vectors, recall I mentioned that we add them tip to tail. So at the tip of A, by the way, this is the tail of a vector, the arrowhead is the tip. From the tip of A, we are now going to draw vector B, but we're not adding it, we're subtracting it, which means we need to flip the direction of B. So it is going to become up. And now we are going to draw vector B, but pointing up. So 3 meters up. And now the total vector starts from here and ends here. 5 plus 3 is 8. And both of these point up, so our direction is simply up. Algebraically, you would have put down 5 meters up minus, this was 3 meters down, so it was a negative 3. Don't flip the sign of the vector here. Because there's a subtraction sign, these will automatically make 2. So you don't flip the sign of the negative 3 even though we flipped it in the drawing. Add it as it is, which is a negative 3. The negative sign here will make it a positive. So 5 plus 3 will give you 8 meters up. And that is how you add or subtract a vector. See how we didn't really subtract the vector here, we just added the negative of the vector. So this might also be written as A plus negative B, meaning the opposite of our vector, B. Next, let's move on to multiplication. The first type of multiplication we are going to discuss is multiplying a vector by a scalar value, otherwise known as scalar multiplication. So say we have vector A, just like in the last example, and it was 5 meters up. Remember, a scalar is just a number. there is no direction associated with it. So scalar multiplication is multiplying your vector by a number, such as 3 times a. What would 3 times 5 meters look like? Let's redraw it. We have a, which was 5 meters, and then we'll have another a and another a, which are also both 5 meters up. So your total vector becomes 15 meters up. If you were to do this algebraically, instead of drawing out the arrows, all you would do is multiply 3 by the magnitude of vector a, which is 5. And 3 times 5 is 15 meters up. The direction that the vector is currently in is the direction that your answer should be in. So if this was 5 meters down, your answer should be 15 meters down. You can also add vectors that are multiplied by scalars. So for example, say I have vector b from our last example, which was 3 meters down. How would I find 3a plus 2b? Let's do this graphically. So we already drew 3 times our a vector right here. And remember, we add vectors tip to tail. So on top of this, I'm going to draw 2 times our b vector, which was only 3 meters. So there's one b, and there's another b. How much of the remaining a vector is left? We had 15 meters, and we subtracted 6 of them. So our answer is just 9 meters up. If you did this algebraically, it would be 3 times the magnitude of vector a, which is 5, plus 2 times the magnitude of vector b, which is negative 3. Because remember, when we put vectors into equations, we can't add an up or a down. We have to add positives and negatives. So instead of writing 3 meters down in the equation, we convert it to negative 3. So we have 15 minus 6, which gives us 9 meters down. Note that there is no vector division. Instead, you can multiply by a fraction. For example, if I wanted to divide vector a by 2, I can multiply it by 1/2. And 1/2 times a will give me half of vector a. Next, let's talk about the dot product. The dot product will give us a scalar answer. Let's say we have vector a, which is equal to a1, a2, and a3. And we have a vector b, which is b1, b2, and b3. The dot product would be equal to a dot b. Usually, this dot is used as a multiplication, but once you get to vectors, this dot actually means dot product, so don't confuse it as a multiplication sign. A dot b is going to be equal to a1 b1 plus a2 times b2 plus a3 b3, which is the same as the magnitude of a times the magnitude of b times cos of theta. Theta is the angle between vectors a and b. Note that the dot product of b and a is the same as a dot b. It doesn't matter if you flip it around, as long as the variables are the same. Let's do an example with finding the dot product. So let's say I have vector a and vector b. In order to find a dot b, I need to multiply a1, which is 5, times b1, which is 1, plus a2 b2, so a2 is 2 and b2 is 2, plus a3 times b3, which is 3 times 1. Because I don't know the angle between these two vectors, I wouldn't be able to use this definition. So adding all these together, you get. So the answer to our dot product is 12, and note that it's a scalar with no direction. Now let's try an example using the dot product when we have to use this definition instead. Say we are given two vectors a and b. Vector a has coordinates of 5, 2. Vector b has coordinates of 6, 1. And the angle between the two is 40 degrees. So in order to find the dot product, because we are given the angle, we should use the equation magnitude of a times magnitude of b times the cos of theta. Note that both of these vectors start from the 0, 0 position. First thing we can do is fill out the cos of theta because theta is 40 degrees. Recall that the magnitude equation is the square root of x2 minus, let's label each of our coordinates. 0, 0 is going to be x1 and y1, and 5, 2 is going to be x2 and y2. Plugging these into our equation, we get the square root of 29. So that means from 0 to point A, that means the magnitude or length of vector A is the square root of 29. Now, let's label vector B x2 and y2, and the beginning coordinates are still x1 and y1. Plugging these into our equation, we get the square root of 37. That means that the length of this vector is the square root of 37, which I'm just going to leave in radical form. Now we can find the dot product. It is just equal to the square root of 29 times the square root of 37 times cos of 40 degrees. You can leave it like this or put it into your calculator to get 25.09 as your final answer. And that is how you would use both dot product equations depending on what you're given. Now let's move on to the third type of multiplication, which is the cross product. Suppose we have vector A and vector B. Let's write these out into ijk form first. 2i minus 3j plus 4k, and negative 1i or negative I plus 2j plus 3k. To do the cross product, we are going to set it up like this. We always put I, j, and k along the top, and the values are going to go underneath. So we have 2i minus 3j and 4k, and then we have negative 1i plus 2j and 3k. So the i's are in this column, and j's in this column, and k's in this column. So make sure when you write out your ijk equation, it should be i's first, followed by j's, then followed by k. So how do we find the cross product with this? So the first step is to cross off the I row, and we're going to rewrite the j and k row, but you can drop the letters. And we put an I next to this. Next, we put a subtraction sign, and this should always be subtraction. We will do the matrix while crossing off j and using just I and k. 2, 4, negative 1, 3. And what you're going to put next to it is a j. Then we plus, and this is always a plus, and we do the matrix for k. And now we cross off k, but we are going to make a matrix for I and j. So 2, negative 3, negative 1, 2. Now, we are going to multiply each of the numbers in this matrix like so, in this direction. So this is how we do that. Multiply negative 3 by 3, then we subtract it from the multiplication of 4 times 2. And that is our I bracket. Next, we keep the subtraction sign. We multiply 2 times 3 and subtract from it 4 times negative 1. Next, we keep the positive sign. This is j. We keep the addition sign, and now we're going to add to it 2 times 2 and subtract from it negative 3 times negative 1. Okay, now we have negative 3 times 3 is negative 9 minus 8i minus 6 minus negative 4j plus 4 minus negative 3 times negative 1, 3k, which is negative 17i minus 10j plus 1k. This is the answer to the cross product. Notice that the cross product gives you a vector answer. Sometimes the cross product is also called the vector product. So that's all for today's video. If you have any questions, leave them in the comments below. I'll be leaving timestamps in the description box below, as well as a link to the related blog post for this video. at my website, thestemtutor.org. Bye for now.